Throughout history, a few structures have pushed engineering so far beyond what anyone thought possible that they stopped being just buildings, bridges, or entertainment venues. Instead, they became monuments telling the stories of how human ambition broke the barriers of engineering throughout history. From lost cities to artificial waterways across continents, and from ancient pyramids to modern skyscrapers towering over skylines, these 16 megaprojects changed the world and stand today as the wonders of the world. In 1930, with America in economic freefall, unemployment climbing past 25%, and businesses collapsing by the thousands, however, at the same time, 3 skyscrapers were locked in the race to become the tallest building in the world. The 40 Wall Street, initially known as Manhattan Company Building, and Chrysler Building were being constructed simultaneously, only kilometers apart from each other. Former business partners turned rivals. Harold Craig Severance and William Van Allen were the main architects on the 2 projects. Harold Craig was building 40 Wall Street that was planned to become the next head office for the Manhattan Company and the tallest building in the world. Meanwhile, William Van Allen was working with Walter Chrysler, America's automobile giant, who wanted to build something even bigger. He wanted a tower that would rise higher than any other structure ever seen. Locked in a competition, the Manhattan Company building reached a final height of 281 meters. But that record was soon broken, as the Chrysler building added a 38-meter spire at the top to reach 319 meters. However, just a few blocks away, former General Motors executive John Jacob Raskob was planning something even bigger. It was the Empire State Building. Born through a rivalry between businessmen, it would go on to become a global icon over the next century. The site on 34th Street was cleared by demolishing the original Waldorf Astoria Hotel, one of the grandest buildings in New York. Demolition finished in late 1929. The stock market crashed weeks later. Construction began in March 1930 anyway. What followed was, by any honest measure, one of the most extraordinary construction feats ever attempted. The original design for the Empire State Building had 50 floors. However, Raskob wasn't willing to accept second or third place and kept on adding more floors. During construction, the design was changed 15 times to finally incorporate more than 100 floors. Despite the race to build taller, the constant design changes, and the economic downturn, the construction timeline was very ambitious. The target was 410 days from groundbreaking to completion. At the time, serious engineers considered that timeline a fantasy. A building of that scale typically took years. For comparison, the Chrysler Building was completed over 7 years. The Empire State Building's developers went on to smash all conventional engineering wisdom. They engineered the entire supply chain around speed. Steel was fabricated in Pittsburgh and shipped to Manhattan on a schedule so precise that each shipment arrived floor by floor, just as the workers above needed it. Nothing sat in storage. There was no room for it. At peak construction, 3,400 men worked the site simultaneously across multiple floors, going up at the same time. The building rose at more than 4 floors per week. 5 workers died during construction, a number far lower than anyone familiar with the conditions would have predicted. They finished 12 days ahead of schedule. The total cost came to just under $41 million in the Depression-era economy. In today's terms, it's roughly $700 million. What makes that figure remarkable is that the original budget was higher. The economic collapse actually drove down the cost of labor and materials so sharply that the project came in under its own estimates, even while going faster than planned. The Empire State Building opened on May 1, 1931. President Hoover switched on the lights by telegraph from Washington. The world took notice as the Empire State Building reached a height of 381 meters to the roof. An antenna spire was added to the top of the building, taking its height to 443 meters. But as iconic as the Empire State Building was, it felt like a disaster early on as almost nobody moved in. The Depression had gutted Manhattan's commercial real estate market completely. Offices sat empty across the city, and the Empire State Building, designed to house tens of thousands of workers, was chronically, embarrassingly vacant. New Yorkers nicknamed it the Empty State Building. For years, observation deck ticket sales were the primary thing keeping the finances afloat. The building didn't turn an actual profit until 1950, nearly 2 decades after opening. There was also the mooring mast. Roscoe had added it to the roof partly to guarantee the height record, and partly because he genuinely believed transatlantic airships would dock there, allowing passengers to descend directly into Midtown Manhattan. The physics of mooring a massive hydrogen airship above one of the windiest urban environments on the planet proved catastrophic in practice. It was used for one semi-controlled public docking and quietly converted into a broadcast antenna shortly after, which turned out to be considerably more useful. The building held the world height record for 41 years. Nothing touched it until 1972, when the North Tower of the World Trade Center surpassed it. Since then, roughly 20 buildings worldwide have exceeded it, including the Burj Khalifa in Dubai, which stands more than twice as tall. In the relentless arithmetic of skyscraper records, the Empire State Building has long since been left behind, and yet it remains the most recognizable building on Earth. That's not sentiment. It shows up in studies, in surveys, in the simple fact that its silhouette is understood globally by people who couldn't point to New York on a map. As soon as it was commissioned, the Empire State Building became a pop culture icon and has remained that way ever since. King Kong climbed it in 1933, 2 years after it opened, and that image burned itself into popular culture permanently. Cary Grant waited at the top in a film that turned the observation deck into shorthand for romantic longing. It has appeared in more movies than any other building in history, not as a backdrop, but as a character, a fixed point, the thing the camera finds when it wants to say, "This is New York." In 1994, the American Society of Civil Engineers named it one of the 7 wonders of the modern world, recognition not just of its height, but of the construction achievement behind it, the speed, the precision, the sheer organizational complexity of raising 102 floors in 410 days with 1930s technology. That's what earned it the designation, not what it looks like, what it took to build it. Around 4 million people visit each year. The steel frame is unchanged from 1931. On a clear day, you can see it from 50 miles out. What it is, underneath all of that, is a building that had no business succeeding. Built at the worst possible economic moment, by men motivated by ego rather than demand, into a market that ignored it for 2 decades. It survived all of that and has become synonymous with New York ever since. Just like another tower in North America, that has come to define an iconic skyline. For most of the 20th century, Toronto had a problem that became a regular hindrance over the years. The city was growing fast. New skyscrapers were going up across downtown through the 1960s and early 70s, and every one of them was doing the same thing, interfering with television and radio signals across the region. The taller the buildings got, the worse the interference became. Broadcasters were losing signal, communications were degrading. The city's own growth was strangling its ability to communicate. The solution, proposed by the Canadian National Railway in 1972, was to build a single transmission tower so tall it would clear every rooftop in the city by a margin that no future development could threaten. A tower that would solve the problem permanently. What they ended up building held the title of world's tallest freestanding structure for 32 years. The engineering brief was straightforward in theory and brutal in practice. The tower needed to be tall enough, at minimum 300 meters, to broadcast above the existing skyline with room to spare. It needed to be structurally stable in a city that sits in a seismic zone and faces serious wind loads off Lake Ontario. And it needed to be built on a site with difficult soil conditions, right at the edge of the lake, where the ground offers considerably less cooperation than an engineer would like. Construction began in February 1973. Workers poured a massive hexagonal concrete base and sank it deep enough to anchor the structure against the lateral forces a tower of this height would face. The concrete shaft above it, hollow, hexagonal in cross-section, reinforced with thousands of tons of steel, was poured continuously using a technique called slip forming. A circular platform slowly climbed the structure as the concrete was poured, allowing crews to work around the clock without stopping. Any interruption risked a structural weakness in the concrete, which in a tower of this scale was simply disastrous, which slowed down construction to a speed of roughly 1 meter per day. At 447 meters, the main shaft was complete. Above that, workers installed a steel antenna mast, which pushed the total height to 553 meters, or 1,815 feet. Getting that mast into position required a Sikorsky S-64 Sky Crane helicopter, which made 45 lifts over the course of 3.5 weeks. Each lift had to be precise. At that altitude, wind conditions were unpredictable enough that crews had to abort and reschedule repeatedly. The work was slow, exposed, and offered no margin for error. The whole project took 40 months and cost 63 million Canadian dollars, roughly 350 million in today's terms. It opened in 1976 and immediately became the tallest freestanding structure on Earth, surpassing the Ostankino Tower in Moscow, which had held the record since 1967. Toronto, a city not typically associated with superlatives, suddenly had the most dramatic piece of infrastructure on the planet rising out of its downtown waterfront. The practical function worked exactly as intended. A single centralized transmission point eliminated the signal interference problem across the region. Broadcasters moved their antennas to the tower, and the issue was solved. In terms of pure engineering utility, the CN Tower did precisely what it was designed to do, but what it became in the years after opening was something the Canadian National Railways Planning Department almost certainly didn't model in their original projections. The observation deck drew visitors immediately and kept drawing them. The glass floor, installed in 1994, 342 meters above the ground, became one of the most photographed spots in Canada. The Edgewalk, introduced in 2011, allowed visitors to walk hands-free along the outside of the main pod at 356 meters, attached to an overhead rail by nothing more than a harness and whatever composure they could maintain. Roughly 2 million people visit the tower every year. A significant portion of them choose to stand on glass above a 300-meter drop and stare down. The revolving restaurant at the top completes one full rotation every 72 minutes. On a clear day, the view extends to Niagara Falls and across the lake into New York State. The height record fell in 2007 when the Burj Khalifa's construction in Dubai passed 553 meters on its way to 828. The CN Tower no longer holds the record it was never actually built to hold. It still holds the skyline. Toronto's downtown has continued to grow around it for 50 years. Dozens of towers have gone up in its shadow. The city has become one of the fastest-growing urban centers in North America, with a skyline that changes visibly year on year. And through all of it, the CN Tower remains the fixed point, the thing every aerial shot finds first, the structure that tells you where you are before anything else does. It was built to fix a broadcasting problem. It cost $63 million and took just over 3 years. The problem it was built to solve was fixed immediately and has never returned. Everything else the tower became was unplanned. Next on the list is yet another tall structure that has become the reference point for a city. In 1919, an engineer named Joseph Strauss submitted a proposal to build a bridge across the Golden Gate Strait in San Francisco. The design was, by most assessments, hideous, a clunky hybrid cantilever structure that looked like it belonged over a railway yard rather than one of the most dramatic natural harbors in the world. The city wasn't interested. Strauss spent the next decade lobbying anyway. By the time construction was approved in 1930, the design had been completely overhauled by his chief engineer, Charles Ellis, and architect Irving Morrow, the men who actually gave the bridge its final form. Strauss took the credit. Ellis, who spent months doing the complex mathematical calculations that made the bridge structurally possible, was fired before construction began and received no official recognition for his work for decades. That tension between vision and credit, between ambition and reality, runs through the entire story of the Golden Gate Bridge. The engineering problem was genuinely formidable. The Golden Gate Strait is not a cooperative place to build anything. The channel is over 1,500 meters wide at the crossing point, with currents running at up to 7.5 kilometers per hour. The water is 67 meters deep at the South Tower location. Fog rolls in from the Pacific with enough regularity that visibility drops to near zero for significant parts of the year. The whole region sits in one of the most seismically active zones in North America. And at the time construction was proposed, the longest suspension bridge span in the world was roughly half the distance that the Golden Gate required. Nobody had built anything like it before because nobody had needed to. The strait had functioned as a natural barrier between San Francisco and Marin County for the entire history of European settlement, with ferry services handling the crossing. As the region grew through the early 20th century, the ferries became increasingly inadequate. A bridge was the obvious answer. The engineering required to build one at this particular location was the problem. Construction began in January 1933. The South Tower Foundation, planted directly on the floor of the strait 300 meters from shore, required workers to operate underwater in open ocean conditions with strong currents and poor visibility. A protective fender, a concrete barrier around the base, had to be constructed first, the water pumped out, and then the foundation work completed inside it. It was slow, dangerous, and repeatedly disrupted by the sea refusing to behave predictably. The towers rose 227 meters above the water, stringing the main cables between them, each cable made up of 27,572 individual steel wires, spun in place over months, required techniques that pushed the limits of what the industry knew how to do. Each finished cable was 92 centimeters in diameter and capable of bearing a load that would have seemed fictional to bridge engineers a generation earlier. Strauss was obsessive about worker safety in a way that was genuinely unusual for large construction projects of the era. He mandated hard hats on site at a time when most construction workers considered them unnecessary. He insisted on safety nets strung beneath the roadway during construction, a significant expense that many considered unjustifiable. Those nets saved the lives of 19 men who fell during construction and survived. They became known as the Halfway to Hell Club. 11 men died on the project, 10 of them in a single accident in February 1937, when a scaffold fell through the safety net and took workers with it into the strait below. One man died in a separate incident earlier in the project. The bridge opened on May 27, 1937. 200,000 people walked across it on the first day before vehicles were allowed on. The roadway deflected noticeably under the weight of the crowd, a detail that unsettled onlookers, but was well within the bridge's design tolerances. What happened in the years after opening built the bridge's mythology layer by layer. The color, officially called International Orange, was chosen by Irving Morrow partly for aesthetic reasons and partly because it made the bridge visible in the fog that regularly obscures the strait. The U.S. Navy had lobbied for it to be painted in yellow and black stripes as a visibility aid for shipping. The fact that the bridge is the color it is comes down to an architect overruling the military on aesthetic grounds. In 1987, on the bridge's 50th anniversary, the same idea from opening day was repeated: pedestrian access before vehicles. Around 300,000 people showed up. The wait was so much greater than the 1937 crowd that the bridge's roadway flattened out completely, losing its characteristic upward curve. Engineers had accounted for load but hadn't modeled this particular distribution of it. The bridge held, but it was a closer calculation than anyone had anticipated. Alfred Hitchcock filmed Vertigo on and around the bridge in 1958. It has appeared in more films than almost any other structure in the world. When the fictional version of San Francisco is destroyed in movies, the Golden Gate Bridge goes first, a cinematic shorthand so established it has become a cliché that filmmakers still can't resist. The bridge was named one of the 7 wonders of the modern world by the American Society of Civil Engineers in 1994, recognized specifically for the audacity of its span, the difficulty of its construction environment, and the elegance of a structure that managed to be both a feat of engineering and one of the most beautiful man-made objects in the world. It carries roughly 10 million vehicles a year. It has been repainted continuously since the day it opened, the maintenance crew finishing one end and starting again from the other in a cycle that never stops. The bridge moves. On a hot day, the roadway can expand by over a meter. In high winds, the deck can sway several feet laterally. It was designed to do exactly that. Joseph Strauss died in 1938, a year after the bridge opened. Charles Ellis, the engineer whose calculations made it all possible, lived until 1949 and spent those years largely uncredited. The bridge still has his math holding it up. We now move across the Atlantic to another mega project that saved a country from catastrophic tides. On the night of January 31st, 1953, a combination of a high spring tide and a severe northwestern storm pushed a wall of water into the southwestern Netherlands that the existing defenses simply couldn't handle. Dikes broke in dozens of places simultaneously. Seawater poured into low-lying polders in the dark, while most people were asleep. By morning, 1,836 people were dead. Nearly 100,000 were homeless. Almost 200,000 hectares of agricultural land were submerged in salt water. Entire villages had ceased to exist overnight. The Netherlands had flooded before. The country had been fighting the sea for centuries. Roughly a third of its land sites below sea level, and another third sits barely above it. But 1953 was different. The scale of it, the speed of it, the fact that it happened in a modern European country with existing flood infrastructure. It made the political case for something that engineers had been proposing for years and governments had been deferring. 3 months after the flood, the Dutch government commissioned the Delta Works. The plan was sweeping in a way that's difficult to convey without listing what it actually involved. Over the following decades, the Netherlands constructed 13 major dams, sluices, locks, dikes, and storm surge barriers across the river delta in the southwest of the country. The objective was to shorten the Dutch coastline by 700 kilometers, eliminating the most vulnerable stretches of open water that had allowed the 1953 storm to do what it did. The engineering challenges varied dramatically from structure to structure, which is part of what makes the Delta Works remarkable as a collective achievement. Some sections required straightforward dike reinforcement. Others required closing open sea channels several kilometers wide in water depths that made conventional construction methods unworkable. The Oosterscheldekering, the Eastern Scheldt storm surge barrier, became the centerpiece and the hardest problem. Engineers had originally planned a closed dam across the estuary, which would have been simpler to build. Environmental opposition in the 1970s forced a redesign. What replaced the original plan was a structure of considerably greater complexity, a semi-permeable barrier with 62 massive concrete piers supporting steel gates that sit open under normal conditions, allowing tidal flow and preserving the estuary's ecosystem, and close automatically when storm surges threaten. The piers alone weighed up to 18,000 tons each. Moving them into position required purpose-built vessels that didn't exist before the project. The Dutch had to design and construct the ships needed to build the barrier before they could build the barrier itself. The gates, each one the size of a house, were engineered to withstand the full force of a North Sea storm, while operating reliably after sitting open in saltwater for years between closures. It took 10 years to build and cost the equivalent of several $billion in today's terms. It is, by most engineering assessments, the most technically complex flood defense structure ever constructed. The Maeslandkering, completed in 1997 as one of the final components of the Delta Works, protects Rotterdam, one of the largest ports in the world. It consists of 2 enormous hollow steel arms, each the length of the Eiffel Tower laid on its side, hinged on either bank of the waterway. Under normal conditions, they sit open in dry docks on each bank, completely invisible to shipping. When a storm surge is forecast, they swing out, meet in the middle of the channel, and seal it. The entire operation is automated, triggered by a computer system with no human intervention required once the decision to close is made. They have closed in earnest a handful of times since 1997. Each time, a structure roughly the size of 2 Eiffel Towers has silently swung shut across one of the busiest shipping lanes in Europe, held back the sea, and then reopened. Since the Delta Works were completed, the Netherlands has not experienced a major flood disaster. The 1953 flood killed 1,836 people. The infrastructure built in response has protected millions. What makes this wonder different from every other on the list is that most people will never see it. There is no observation deck. There is no famous silhouette. The Eastern Scheldt barrier is impressive if you know what you're looking at, but it doesn't photograph like a bridge or a tower. It sits in the water and does its job. In a country where the alternative is the sea reclaiming the land entire generations built their lives on, doing its job is enough. In 1962, Brazil and Paraguay shared a border, a river, and almost nothing else in common. Brazil was the largest country in South America, resource-rich and growing fast. Paraguay was one of the smallest, landlocked, and poor in ways that went beyond economics. The idea that these two countries would agree on anything ambitious was optimistic. Then someone looked seriously at the Paraná River. The Paraná is one of the great rivers of South America, 4,880 kilometers long, draining a basin larger than Western Europe. Where it runs along the border between Brazil and Paraguay, it drops in elevation in a way that had been catching engineers' attention for decades. The hydroelectric potential at the right location on that stretch of river was, by any calculation, enormous. The question was whether the two countries could agree on how to develop it. In 1973, after years of negotiation, they signed the Itaipu Treaty. Construction began the following year. What came next was one of the largest construction projects in recorded history. Before a single concrete pour could begin, the engineers faced a problem that had no straightforward solution. The Paraná River was still flowing. At the Itaipu site, it moved 8,500 cubic meters of water per second on average, surging far higher during seasonal floods. Building a dam across an active river of that volume meant the river had to go somewhere else first. The solution was to dig a bypass channel, 2 kilometers long, 150 meters wide, 90 meters deep, cutting through solid rock beside the construction site. Moving that volume of rock required 50 million tons of earth and stone to be excavated. The bypass channel alone, before a single dam structure was started, was an engineering project larger than most things built at the time. Then they diverted the river into it and built the dam in the dry. The main dam structure stretches 7.9 kilometers across the river. The powerhouse contains 20 generating units, turbines so large that each one individually could power a mid-sized city. The reservoir behind it holds 29 billion cubic meters of water, flooding an area of 1,350 square kilometers. An artificial lake that drowned several towns, displaced around 40,000 people, and submerged a set of waterfalls called the Guaíra Falls, which had been among the most spectacular in the world. The Guaíra Falls are gone. They exist now only in photographs. Construction ran from 1975 to 1984. At peak activity, 40,000 workers were on site. Over the life of the project, roughly 150 workers died. The total cost reached approximately $19 billion, making it, at the time of completion, one of the most expensive construction projects ever undertaken. What it produced was a generating capacity that was, for a period, without parallel anywhere on Earth. Itaipu's 20 turbines can produce 14,000 megawatts of power. In 2016, it set a world record by generating 103.1 terawatt-hours of electricity in a single year, more annual electricity production than any power plant in history at that point. For decades, it supplied roughly 80% of Paraguay's entire electricity needs and around 17% of Brazil's. A single dam on a shared border powering most of one country and a significant fraction of another simultaneously. The economics of the arrangement have never been entirely comfortable. Under the original treaty terms, Paraguay, which uses a fraction of the power Itaipu generates, sells its surplus share back to Brazil at a fixed price set in 1973. For decades, Paraguay argued those terms were exploitative, locking a small, poor country into a contract that paid them far below market value for energy produced on their own territory. Renegotiations have happened. The tension has not fully resolved. Being named one of the 7 wonders of the modern world is a recognition that the scale of the engineering, the diversion of one of the world's major rivers, the construction of a 7.9-kilometer dam, the installation of a power generation system of that capacity represented something genuinely without precedent at the time it was built. The Chinese Three Gorges Dam, completed in 2003, eventually surpassed Itaipu in both installed capacity and annual generation. Itaipu no longer holds the records it once did. What it still holds is the river. The Paraná runs through the turbines today, as it did the day they switched them on. The bypass channel cut through solid rock in the 1970s still sits beside the dam, empty now, a ghost of the engineering problem it was built to solve. The towns beneath the reservoir are still down there, somewhere under 29 billion cubic meters of water. And the Guaíra Falls, which once thundered loud enough to be heard from miles away, are silent. Next up, we have a megaproject that was planned over a century and finally breached the waves to connect Europe. The idea of a tunnel under the English Channel is older than most people assume. A French engineer named Albert Mathieu proposed one in 1802, a horse-drawn carriage tunnel lit by oil lamps, with an artificial island in the middle of the channel for ventilating the thing. Napoleon expressed interest. The British, characteristically, did not. Over the following 180 years, the tunnel was proposed, studied, started, and abandoned more times than anyone involved would have liked to count. Work actually began twice, once in 1880 and again in 1974, before being stopped on both occasions by British political opposition, rooted in a single, consistent anxiety that a fixed link to continental Europe represented a threat to the island's security that no amount of engineering benefit could justify. It took until 1988 for construction to finally begin in earnest. By then, the original concept had been refined, revised, and debated for the better part of 2 centuries. The geology under the channel turned out to be one of the few cooperative elements of the entire project. A layer of chalk marl, dense, relatively impermeable, consistent in depth, ran beneath the seabed at a workable depth for most of the crossing. It was almost as if the ground had been designed for tunneling, which made the work faster and more predictable than comparable projects in more difficult rock. There were 3 tunnels to bore, 2 rail tunnels for passenger and freight trains, and a smaller service tunnel running between them for maintenance access and emergency evacuation. Each one ran 50 kilometers beneath the seabed, connecting Folkestone in Kent to Coquelles near Calais. At their deepest point, they sat 75 meters below the seabed surface. Tunnel boring machines, enormous rotating cutting heads followed by prefabricated concrete lining systems, worked from both ends simultaneously, the British side and the French side boring toward each other. The alignment had to be precise enough that when the 2 sides met in the middle of the channel, the tunnels would connect within acceptable tolerances. The survey work required for that level of accuracy across 50 kilometers under the sea, using 1980s technology, was itself a significant achievement. They met in December 1990. The 2 boring machines, approaching from opposite directions, were off by 358 millimeters horizontally and 58 millimeters vertically across 50 kilometers of tunneling. That is approximately the width of an adult hand. The project employed 13,000 workers across both sides at peak construction. 10 workers died during the build, a number that, like the Empire State Building and the Golden Gate Bridge before it, was lower than the scale of the project might have suggested, but is still 10 people who didn't go home. The cost, however, was a disaster. The original budget estimate was £4.8 billion. Final costs came in at £4.65 billion for construction alone, apparently within range until you account for the financing costs, cost overruns during construction, and the additional capital required when the project ran into difficulties. Total costs reached approximately £10 billion, more than double the original projection. The private consortium that financed the tunnel, Eurotunnel, carried a debt burden that pushed it to the edge of insolvency multiple times in its early years. It underwent a major financial restructuring in 1995, a year after opening. The tunnel opened in May 1994. The first official passenger service ran on November 14th of that year. What had taken 180 years of proposals, false starts, and political obstruction to build was suddenly carrying passengers between London and Paris in around 2.5 hours. The operational history has been eventful in ways that the original projections didn't fully model. A fire broke out in the tunnel in 1996, 2 years after opening. Started by a truck on a freight shuttle. No passengers died, but the damage was significant, and one of the 3 tunnels was closed for months. A second serious fire occurred in 2008. The tunnel's designers had built in the service tunnel specifically for emergencies, and both times it performed as intended. But fire in an enclosed space 75 meters under the seabed is a category of emergency that concentrates the mind. The migration crisis of the mid-2000s brought a different kind of problem. Thousands of migrants attempting to reach Britain gathered near the French entrance to the tunnel and repeatedly attempted to access it on foot, creating security situations that temporarily disrupted services and generated significant political friction between Britain and France. A version of exactly the kind of cross-channel tension the tunnel's 19th century opponents had always feared, though not the kind they had imagined. Eurotunnel, now renamed Getlink, has carried over 500 million passengers since opening. Around 400 trains pass through the tunnel every day. The journey between the two portals takes 35 minutes. In 1994, the American Society of Civil Engineers included the Channel Tunnel on its list of 7 wonders of the modern world, recognizing the bored length beneath open water, the precision of the alignment, and the completion of a project that had defeated every previous attempt for the better part of 2 centuries. Channel Tunnel proved to be more complex than anticipated and billions over budget, the same problems that plagued the next megaproject on our list. Ferdinand de Lesseps was the most celebrated engineer in the world. When he arrived in Panama in 1881, he had just completed the Suez Canal, a project widely considered the greatest engineering achievement of the 19th century. More than 1.5 million workers had taken part in building the 193-kilometer-long canal. It took 10 years to build and elevated France's reputation across the globe. Compared to the Suez, the Panama Canal was supposed to be simpler. It was half the size, and the chief engineer had already set a record. While the Suez had been dug through flat desert, Panama was a narrow isthmus. It would take less time, less labor, and could be built at a much lower cost. However, the confidence was misplaced. De Lesseps had decided on a sea-level canal, no locks, just a straight cut through the isthmus at ocean level, the same approach that had worked in Egypt. The problem was that Panama was not Egypt. The terrain between the Atlantic and Pacific coasts was not flat desert, but dense jungle sitting on top of a mountain range. The Culebra Cut, the section through the Continental Divide, required excavating through rock and unstable soil to a depth that made the Suez Canal look like a drainage ditch. Then there was the water. Panama receives around 2.5 meters of rain annually. The Chagres River, running directly across the proposed canal route, flooded with a violence during wet season that repeatedly overwhelmed the excavation sites, washing away equipment and work in hours that had taken weeks to complete. De Lesseps's engineers dug, the jungle and the rain filled it back in, and then people started dying. Yellow fever and malaria moved through the workforce with a speed that no one had fully anticipated. The actual death toll from the French effort remains disputed. Estimates run from 20,000 to as high as 22,000 workers dead over the course of the project, most from disease rather than accidents. The French tried to keep the scale of the mortality quiet. The workers arriving to replace the dead often didn't know what had happened to the men before them. It also proved to be vastly more expensive, and the Lesseps's company went bankrupt trying to raise the required funds. Public confidence had evaporated, and the French effort collapsed in 1889. De Lesseps and his sons were convicted of fraud and corruption. He died in 1894 without ever returning to Panama. Despite wasting close to $100 billion, the excavation sites were abandoned. A decade later, the project had a new bidder. The U.S. President Theodore Roosevelt considered a canal across Panama a strategic necessity and swiftly pushed it through Congress. He secured the assets related to the abandoned canal for $40 million in 1904. The Americans made 2 decisions that changed everything. The first was to abandon the sea-level approach entirely and build a lock canal instead, using the Chagres River rather than fighting it by damming it to create Gatun Lake and floating ships across the elevated interior on a system of locks. The second was to solve the disease problem before doing anything else. Dr. William Gorgas spent 2 years on a systematic mosquito eradication program before major construction began. fumigating buildings, eliminating standing water, screening hospitals, and doing the painstaking epidemiological work that dramatically reduced yellow fever and malaria transmission across the canal zone. It was unglamorous work that saved thousands of lives and made everything that followed possible. Construction proper ran from 1906 to 1914. The Culebra Cut, the same section that had defeated the French, was the central challenge. Workers blasted and excavated through 9 kilometers of rock and unstable soil in conditions that remained brutal even after the disease problem was brought under control. The hillsides on either side of the cut were prone to landslides that could bury weeks of work in minutes. The excavation was restarted repeatedly. At peak construction, 40,000 workers were on site. Around 5,600 died, a fraction of the French toll, but still an enormous human cost. The canal opened on August 15, 1914. A cargo ship called the SS Ancon made the first official transit. Almost nobody noticed. The First World War had broken out 11 days earlier, and the world's attention was elsewhere. What the canal did to global shipping was immediate and permanent. The route from New York to San Francisco, previously requiring a journey around the southern tip of South America, 22,500 kilometers, dropped to 9,500 kilometers. Ships that previously spent weeks at sea saved weeks. Commodities that had been prohibitively expensive to transport became viable. The economics of global trade shifted visibly within years of opening. The canal became the object of political tension almost immediately. Panama spent decades trying to renegotiate the terms under which the United States controlled the canal zone. The process was bitter, protracted, and occasionally violent. In 1977, President Carter signed the treaties that agreed to transfer control to Panama. On December 31, 1999, the United States handed over the canal. Panama has operated it since without incident. The scale of the excavation, the complexity of the lock system, and the fact that the project was completed at all makes it one of the most challenging engineering efforts in history, which is probably why it made its way to the list of 7 wonders of the modern world. An expansion project completed in 2016 added a 3rd set of locks, allowing the canal to handle the massive container ships that the original 1914 design couldn't accommodate. The new locks can pass ships carrying 14,000 containers. Around 14,000 ships transit the canal every year. Each crossing takes between 8 and 10 hours. The canal generates around $2 billion annually for the Panamanian government. De Lesseps' original excavation is still down there somewhere, buried under decades of American and Panamanian expansion, absorbed into the walls of the cut that finally defeated him. The BBC, in 2003, added 2 structures to the civil engineering wonders list that the ASCE had left off. One of them had been holding back the Colorado River since 1935. The other had been connecting Manhattan to Brooklyn since 1883. The argument for including both was difficult to dispute. For 13 years, a man named John Roebling tried to convince the city of New York to let him build a bridge across the East River. The crossing between Manhattan and Brooklyn had relied on ferry services for the entirety of both cities' existence. In winter, when the river froze, the ferries stopped. People were stranded. Commerce halted. The case for a bridge was obvious to everyone who needed to cross the river and had been denied by weather or congestion. The case against it was that nobody believed a bridge of that span was structurally possible. The East River at the proposed crossing is 480 meters wide. In the 1860s, the longest suspension bridge in the world spanned roughly a third of that distance. Roebling was proposing to more than triple the record. He was finally approved in 1869. 2 months later, before construction began, he was standing on a dock surveying the site when a ferry struck the pier he was standing on. His foot was crushed. He refused hospital treatment, insisted on directing his own care using a hydrotherapy method he personally believed in, and died of tetanus 3 weeks later. His son Washington took over. Washington Roebling was 32 years old when he inherited one of the most complex engineering projects ever attempted. He had worked alongside his father long enough to understand the design, but nothing had prepared him for the particular challenge that would define the next decade of his life: the caissons. To anchor the bridge's 2 towers, workers had to excavate down through the riverbed to reach bedrock. The method was pneumatic caissons, massive airtight wooden chambers sunk to the riverbed, pressurized with compressed air to keep the water out, with workers inside digging by hand. As the caisson sank deeper, the air pressure inside had to increase to match the water pressure outside. Nobody fully understood decompression sickness in 1870. Workers who spent hours under high pressure and then returned too quickly to normal atmospheric pressure developed what they called caisson disease, agonizing joint pain, paralysis, and in some cases, death. Over the course of the Brooklyn Bridge's foundation work, roughly 110 workers suffered serious cases. 3 died. Washington Roebling himself went down into the caissons repeatedly to supervise, developed severe caisson disease, and never fully recovered. By 1872, he was bedridden. He would remain largely housebound for the rest of the construction. From his apartment in Brooklyn Heights, Washington Roebling watched the bridge go up through a telescope. His wife Emily, who had no formal engineering training, became the critical link between the bedridden chief engineer and the construction site. She learned enough engineering to carry his instructions to the site supervisors, relay technical problems back to her husband, and communicate decisions with enough authority that the project continued to function. For over a decade, she was, in practical terms, the bridge's operational manager. When the Brooklyn Bridge opened on May 24, 1883, Emily Roebling was the first person to cross it, by carriage, carrying a rooster as a symbol of victory. Washington watched from his window. The bridge had taken 14 years and cost $15.5 million, roughly $500 million in today's terms. 27 workers died during construction. What opened that day was, by a significant margin, the longest suspension bridge in the world, its central span of 486 meters, nearly doubling the previous record. The towers rose 83 meters above the river, making them the tallest structures in the Western Hemisphere at the time. The steel wire cables supporting the deck, each one containing 5,434 individual wires, were a new technology, replacing the iron wire used in previous suspension bridges and allowing a strength-to-weight ratio that made the span possible. 6 days after opening, a rumor spread through a crowd on the bridge that it was about to collapse. The resulting stampede killed 12 people. The bridge was undamaged. P.T. Barnum, apparently recognizing an opportunity to make a point, led 21 elephants across it the following year to demonstrate its stability. The bridge's grip on New York's identity set in quickly and has never loosened. Hart Crane wrote a long poem about it in 1930. The painter Joseph Stella depicted it repeatedly, obsessively, as a kind of industrial cathedral. It has been the backdrop for more photographs of New York than perhaps any other single structure, the towers and cables framing the skyline in a composition that has remained essentially unchanged for 140 years. A German saboteur planted a bomb on it during the First World War. It survived. It survived the construction of the Manhattan Bridge and the Williamsburg Bridge, both of which offered competing crossings and neither of which diminished its stature. It survived the 20th century, the transformation of the waterfront around it, the collapse of the World Trade Center, visible from its walkway on September 11, 2001. It carries around 100,000 vehicles and pedestrians every day. The walkway above the traffic lanes is one of the most walked paths in New York, offering a view of the harbor and skyline that has drawn people since the day it opened. Washington Roebling lived until 1926, long enough to see the bridge outlast every skeptic who had said it couldn't be built. He gave almost no interviews about it. When asked about the bridge late in his life, he was characteristically brief. He had spent 14 years building it and another decade recovering from building it. The BBC in 2003 added 2 structures to the civil engineering wonders list that the ASCE had left off. One of them had been holding back the Colorado River since 1935. The other had been connecting Manhattan to Brooklyn since 1883. The argument for including both was difficult to dispute, starting with the dam. In the early 20th century, the Colorado River was one of the most dangerous rivers in the American West. Not dangerous in the way people romanticize wild rivers, dangerous in a practical, economically devastating sense. Every spring, Snowmelt from the Rockies sent the river into violent flood, destroying farms, wiping out irrigation infrastructure, and making any kind of reliable agriculture across the southwestern desert essentially impossible. Then, in the dry months, it would slow to a trickle, leaving the same farmers without water entirely. The river gave nothing on a predictable schedule. It flooded when you didn't need it and disappeared when you did. 7 states depended on the Colorado. All 7 had competing claims on its water. Getting them to agree on anything required the kind of negotiation that takes years and still ends with everyone mildly dissatisfied. The Colorado River Compact of 1922 divided the water between the upper and lower basin states. What it didn't do was solve the flooding, the drought cycles, or the absence of any infrastructure capable of storing water at the scale the region needed. A dam at Boulder Canyon, later moved to Black Canyon, was the proposed solution. In 1928, Congress approved it. Construction began in 1931. The Black Canyon site on the Nevada-Arizona border was, in the summer, one of the most hostile construction environments in the country. Temperatures inside the canyon regularly exceeded 50 degrees Celsius. The canyon walls were sheer and unstable. The Colorado at that location was moving fast, and before any concrete could be poured, the river had to be diverted through 4 tunnels, each one over a kilometer long, bored through the canyon walls on either side. That diversion alone took 8 months. The dam itself was an engineering problem that had no direct precedent. The volume of concrete required was 2.6 million cubic meters, enough to build a 2-lane highway across 5,000 kilometers. Unprecedented for a single structure, that volume of concrete poured as a single mass would generate heat that would have taken over a century to dissipate and cracked the structure in the process. The solution was to pour it in interlocking columns of smaller blocks, with refrigerated pipes running through each one to draw the heat out artificially. The columns were then grouted together once cooled. It worked, but it required a cooling system built into the dam itself. At peak construction, 5,000 men worked the site around the clock in 3 shifts. The canyon offered no natural shade and temperatures that made sustained physical labor genuinely life-threatening. Workers were paid Depression-era wages to do it anyway, because the alternative was no wages at all. According to official figures, 96 workers died during construction, which excludes deaths attributed to heat and carbon monoxide poisoning in the diversion tunnels that the company listed under other causes. The dam was completed 2 years ahead of schedule in 1935. What it created was immediate and transformative. Lake Mead, the reservoir behind the dam, is the largest reservoir in the United States by volume, stretching 177 kilometers behind the dam wall and holding enough water to cover the entire state of Pennsylvania to a depth of around 30 centimeters. The hydroelectric plant embedded in the dam's base generates 4,000 megawatts of power, supplying electricity across Nevada, Arizona, and California. The controlled release of water downstream made large-scale agriculture viable across the desert Southwest in ways that had been impossible before. Las Vegas, 48 kilometers away, exists in its current form largely because of what Hoover Dam made possible. The power, the water, the economic activity generated by construction. The city's modern trajectory begins in the canyon downstream. The dam itself is 221 meters tall and 379 meters wide at the crest. At its base, it is 200 meters thick. It weighs approximately 6.6 million tons. The Colorado River has not flooded uncontrolled downstream since the dam closed its diversion tunnels in 1935. There are 2 bronze sculptures at the dam's entrance, Art Deco figures called the Winged Figures of the Republic, installed at dedication. Between them is a terrazzo floor inlaid with a star map marking the exact astronomical positions of the planets on the day Franklin Roosevelt dedicated the dam, September 30th, 1935. The idea was to give any future civilization that found the site a way to calculate exactly when it was built. The dam draws around 1 million visitors a year. It has appeared in films, been used as a dramatic backdrop, and survived a period in the years after September 2001 when serious security concerns about its vulnerability to attack led to significant changes in public access. A bypass bridge was completed in 2010 specifically to reroute highway traffic away from the dam's crest. The Mike O'Callahan Pat Tillman Memorial Bridge now carries vehicles across the canyon 274 meters above the river, with the dam visible downstream. Standing on that bridge and looking back at the dam, what strikes most people isn't the size, though the size is staggering. It's the setting, the sheer canyon walls dropping to the river, the geometric perfection of the concrete curve against the raw rock, the absolute improbability of something that precise existing in a place that hostile. It has been holding back the Colorado River for nearly 90 years without interruption. Since their creation, many of these structures have been surpassed by even bigger construction projects. But these engineering wonders of the world continue to be the reference point for what human ambition can create in a quickly shifting world. More than 4,500 years ago, something unbelievable happened on the edge of the Sahara Desert. In 2600 BC, on the western bank of the Nile, Pharaoh Khufu ordered building something that would outshine every other structure on Earth for 4,000 years. It is the only ancient wonder of the world still standing today, the Great Pyramid of Giza. The pyramid rises about 138 meters today, but what we see today is a skeleton. Originally, it was even taller. When it was completed, the entire exterior was encased in smooth white limestone, polished to a finish so reflective that it could be seen from the mountains of Israel, over 400 kilometers away. It didn't look like a rough, stepped structure. It looked like a solid blade of white light rising out of the sand. At its very tip sat a capstone plated in gold, catching the sun like a mirror held up to the sky. That version of the pyramid no longer exists. Over centuries, the casing stones were stripped away and used to build mosques and palaces across Cairo. What tourists photograph today is the exposed inner core, the scaffolding, essentially, of something that was once almost impossibly beautiful. But none of that is the real mystery. The real mystery is, how did they build such a colossal structure 5 millennia ago? For context, the construction effort to build the Pyramid of Giza involved moving 2.3 million stone blocks with an average weight of around 2.5 to 15 tons each. The heaviest ones, deep in the king's chamber, came from Aswan, 900 kilometers south, and weighed up to 80 tons. That's the equivalent of 12 adult African elephants per block. These stones were then lifted as high as 146 meters, with no cranes, no steel, no engines. But how could that be possible? On paper, this seems so far beyond what an ancient civilization should be capable of that it has given rise to speculation that this ancient giant was actually built by aliens. However, the archaeological records discovered over centuries tell the story of erecting this ancient marvel. For a long time, people believed slaves built the pyramids under whips and chains. That image became popular through ancient stories and Hollywood movies. But modern excavations near the site tell a different story. Archaeologists found worker villages, bakeries, breweries, organized cemeteries for laborers. These weren't disposable slaves. Many were skilled workers who were fed, paid, and even honored for their work. Most historians believe tens of thousands of laborers worked in rotating crews. During the annual flooding of the Nile, farmers couldn't work their land. That off-season may have allowed the state to mobilize huge workforces. However, the workforce alone does not solve the engineering problems. The first problem that the 20,000 workers on the site had to solve was moving 2.5-ton blocks across desert sand. At that, weight blocks are guaranteed to dig in. The sleds grind to a halt. You can have 1,000 workers and still go nowhere. The Egyptian found a solution to this through simple physics. They wet the sand ahead of the sled to drop friction dramatically. It made the sand more compact, hardened, and helped the sleds glide. Researchers confirmed this in 2014 when they found a tomb painting showing workers pouring liquid in front of a sled carrying a massive statue. But now to the bigger question. How did those blocks move to the height of a 40-story modern skyscraper and were installed as accurately as within 1 degree of error? For centuries, the leading theory involved ramps, a straight ramp running from the base up one side of the pyramid. Simple enough in concept, except when you run the numbers, the ramp itself becomes a problem bigger than the pyramid. To maintain a workable incline, that ramp would need to extend nearly 2 kilometers into the desert. The material required to build it would rival the pyramid's own volume. You'd essentially be building 2 massive structures to end up with one, so maybe a spiraling ramp wrapping around the outside of the pyramid as it rose. More efficient, but then you lose sight of the corners. You can't measure the angles. You can't ensure that 4 sides, each 230 meters long, meet perfectly at a single point at the top. And the Great Pyramid's base is level to within 2.1 centimeters across its entire footprint. That's not an accident. That's the kind of precision that makes modern engineers uncomfortable. In 2003, a French architect named Jean-Pierre Houdin proposed something different. After 7 years of research and 3D modeling, he suggested that the Egyptians used 2 ramps, not one, a straight external ramp for the bottom third of the pyramid, where the blocks were heaviest and most numerous. And then, for the upper 2/3, an internal ramp, a tunnel spiraling upward through the pyramid itself, like a corkscrew hidden inside the structure. It solves the problems the other theories don't. The external ramp stays short enough to be practical, the corners stay visible, and the internal ramp, once construction finished, would simply be sealed, becoming part of the pyramid's interior mass. What makes this more than just an elegant theory is what happened in the 1980s, when the pyramid was scanned using microgravimetry, a technique that measures variations in density. The scan wasn't looking for ramps, it was looking for hidden chambers. It didn't find any, but it did find something else. A spiral of lower density material running through the upper portion of the pyramid, exactly where Houdin's internal ramp would be. No one has been able to get close enough to confirm it. No entrance to any internal tunnel has ever been found, so the evidence, if there is any, sits inside the pyramid, unreachable, giving rise to more and more theories. To this day, no one can tell what happened with 100% accuracy, but as called out by experts, to say that the aliens built this means robbing the ancient civilization of one of humanity's greatest achievements. Something that is difficult to imagine today was built almost 5,000 years ago, and the remnants are still standing to tell their story. But while the pyramids in Egypt have fascinated explorers for thousands of years, humanity has built similar structures across the world, just like the ones on southern Mexico's Yucatan Peninsula. Twice a year, on the spring and autumn equinox, something happens at a pyramid in southern Mexico that has been happening for over 1,000 years. As the sun moves across the sky in the late afternoon, it catches the edges of the pyramid's 9 terraced platforms and casts a series of triangular shadows along the northern staircase. Those shadows, falling one after another in sequence, create the unmistakable silhouette of a serpent descending from the top of the pyramid to the ground, where a carved stone snakehead sits waiting at the base of the stairs. The serpent appears, it holds for a few hours, then the sun moves on and it vanishes. This wasn't a coincidence. The Maya built it that way. They calculated the precise orientation of the pyramid, the exact angle of each terrace, the specific height of every platform, so that on those 2 days each year, the sun would do exactly that. A civilization without computers, without modern surveying equipment, without any of the tools we consider basic to precision construction, engineered a light show into a 30-meter pyramid that still works perfectly today. That is Chichen Itza, and the serpent is just the beginning. Chichen Itza sits in the Yucatan Peninsula in southeastern Mexico, and for several centuries it was one of the most powerful cities in the entire Maya world. At its peak, somewhere between 600 and 1200 AD, it may have been home to over 50,000 people, a metropolis by the standards of any civilization at the time. The city covered nearly 5 square kilometers and contained temples, observatories, ball courts, and marketplaces. It was a political, religious, and commercial center that drew people from across Mesoamerica. Built around 600 AD, the city lies in the middle of one of the most arid stretches of the Yucatan Peninsula, where there are no rivers, no lakes, and rainfall averages just enough to stay alive on. The city exists entirely because of cenotes, the massive natural sinkholes punched through the limestone bedrock by millions of years of groundwater erosion, exposing underground wells below. That's where the city gets its name. Chichen Itza literally means at the mouth of the well of the Itza. Without those sinkholes, there would be no settlement, no pyramid, no empire. The Maya were extraordinary astronomers. Without telescopes, they calculated the length of the solar year to within minutes of what we know today. They tracked Venus across the sky with enough precision to predict its cycles 500 years into the future. Their calendar system was so sophisticated that it's still studied by mathematicians, and all of that knowledge was baked into the architecture of Chichén Itzá. The city had paved streets with cut stone. It had a network of elevated causeways that connected the major structures and extended outward toward neighboring towns. Many European cities during the same period had no concept of paved streets. At the heart of it all stood El Castillo, the pyramid most people picture when they think of Chichén Itzá. The name means the castle in Spanish, which is what the conquistadors called it when they arrived because they had no framework for understanding what it actually was. It wasn't a castle, it was a calendar. El Castillo has 4 sides, each with a staircase of 91 steps. Multiply that by 4 and add the single step of the top platform and you get 365, the number of days in a solar year. Each of the pyramid's 9 terraced levels is divided in 2 by the staircases, giving 18 sections per side, the number of months in the Maya calendar. The pyramid wasn't just a line to the sun, it was a physical representation of how the Maya understood time itself. The Great Ball Court at Chichén Itzá is the largest in Mesoamerica, 168 meters long and 70 meters wide, flanked by walls 12 meters high. The game played there involved a rubber ball that could not be touched with hands or feet. Players used their hips, knees, and elbows to keep it moving and drive it through a stone ring mounted high on the wall. The acoustics of the court are so precise that a whisper at one end can be heard clearly at the other, 168 meters away. What is known is that the ball game carried serious religious weight. It reenacted a Maya creation myth, and losing wasn't just a defeat. Some evidence suggests that the losing team, or possibly the winning team, was sacrificed at the end of major games. Carved reliefs on the court walls showed decapitation scenes. Whatever was happening at that court, it wasn't a sport in the way we understand the word. By the early 13th century, Chichén Itzá had collapsed as a political power. The reasons are still debated: prolonged drought, internal conflict, the rise of competing city-states. The population dispersed, the temples were abandoned, the jungle moved in slowly, swallowing the edges of the city, climbing the walls, filling in the spaces between buildings. When Spanish conquistadors arrived in the 16th century, they found a place that the Maya themselves still considered sacred, still visited for rituals, still feared, but no longer inhabited. The Spanish had little interest in understanding what they found. They destroyed Maya manuscripts, tore down religious objects, and forced conversion on the surviving population. Of the thousands of Maya books that existed, only 4 survived. The knowledge encoded in them was almost entirely lost in a matter of decades. What we know about the Maya today comes largely from archaeology, from the buildings they left behind, and from the handful of written records that weren't burned, which makes what the buildings do tell us even more remarkable. El Castillo, the ball court, the Temple of the Warriors, the observatory they called El Caracol, each one is a piece of a larger intellectual system. They built their knowledge into the landscape so permanently that even centuries of abandonment, conquest, and jungle overgrowth couldn't erase it. From southern Mexico, we move to the world's longest structure in China that was built over centuries. In the 7th century BC, the rulers of northern China had a problem that kept getting worse. From the steppes beyond their borders, nomadic tribes were raiding their settlements. They came fast, on horseback, hit hard, and disappeared before any organized defense could respond. Crops were destroyed, villages were burned, people were taken, and no matter how many soldiers were stationed at the border, the raids kept coming because the border itself didn't really exist. It was just open land, and open land can be crossed from anywhere. The solution that emerged wasn't a military one. It was a construction project. If you couldn't patrol everything, you built something that did it for you. A wall, not around a city, but around an entire civilization. What began as a series of disconnected fortifications built by individual states to protect their own territory eventually became the longest structure ever built by human hands. the Great Wall of China stretches over 21,000 kilometers across mountains, deserts, and river valleys. It passes through more than 400 towns. In some places, it rises to 9 meters high, wide enough at the top for 5 horses to ride side by side. However, the wall that exists today is not the wall that those early rulers built. That version came much later, and the story of why it was rebuilt is as interesting as the story of how it was first constructed. By the 3rd century BC, the warring states of northern China had unified under the Qin dynasty. The first emperor, Qin Shi Huang, connected the existing walls and extended them into a single continuous line of defense. It was an extraordinary undertaking, but the construction was brutal. Hundreds of thousands of workers were conscripted into labor. Supply lines stretched across impossible terrain. Workers who died on site, which many did from exhaustion, injury, and starvation, were buried within the wall itself. The wall became as much a grave as a fortification. And yet, it wasn't enough. Dynasties rose and fell. The wall was breached, abandoned in sections, and left to decay. For nearly 1,000 years, large parts of it crumbled back into the landscape. Then came the Ming dynasty in the 14th century, and with it, the wall that the world knows today. The Ming rulers had good reason to be afraid. They had come to power after expelling the Mongols, who had conquered China and ruled it for nearly a century. The memory of that occupation was still raw, and the threat hadn't disappeared. The Mongols were still out there, still organized, still dangerous. The Ming response was to rebuild the wall on a scale that dwarfed everything that had come before. They didn't just repair what existed, they redesigned it. The new wall was built primarily from brick and stone rather than rammed earth, which made it significantly stronger and more durable. Watchtowers were added at regular intervals, spaced so that a signal fire lit at one tower could be seen from the next, making it a communication system that could relay a warning across thousands of kilometers in hours. The scale of this effort is difficult to fully grasp. Some historians estimate that hundreds of thousands of workers were involved at the project's peak, drawn from across the empire. The logistics of moving materials through mountain terrain, feeding and housing a workforce spread across thousands of kilometers, would challenge a modern government with modern tools. The materials used in the Great Wall's construction differ greatly depending on the kind of terrain the wall passed through and the materials available in the surrounding areas. In many places, rammed soil and wood were used, while the strongest sections of the wall were built using marble and bricks. However, what kept the bricks together through centuries of earthquakes, floods, and freezing winters was something no engineer would think to specify today. The mortar used in Ming-era construction contained sticky rice, cooked, mixed into a paste, and combined with slaked lime to create a binding agent that proved stronger and more waterproof than anything else available at the time. Researchers testing samples from Ming-era sections have found that the rice mortar is still intact, still binding, still doing exactly what it was designed to do 600 years later. The wall worked, up to a point. It slowed raids, controlled movement, and gave the Ming military time to respond to incursions. But it never made China truly secure. In 1644, Manchu forces from the northeast didn't breach the wall. A Ming general opened the gates and let them through. The dynasty fell, and the wall, for all its scale and ingenuity, couldn't protect against that. After the Ming collapse, large sections of the wall were left unguarded and unmaintained. Local villagers quarried its bricks for building material. Farmers plowed up its foundations. Centuries of neglect, combined with harsh weather, eroded significant portions entirely. Today, roughly 1/3 of the original Ming wall has disappeared, not through conquest or demolition, but through simple abandonment. What remains is still staggering. The wall's sheer size has given rise to many popular myths, including the one that it is visible from the moon. However, that is not the case. It has been a popular myth since before humanity's first voyage into space. And when the first person to set foot on the moon, Neil Armstrong, was asked about it, he simply said that no man-made structure was visible from the moon. No one knows exactly how many people died building the Great Wall across all its centuries of construction. Estimates run into the hundreds of thousands. Some of them are almost certainly still inside it, built on human ambition, effort, and sacrifice. The wall has outlasted every dynasty that built it, every threat it was constructed to stop, and every empire that eventually fell on both sides of it. It is still there, crossing the mountains, exactly where they left it. From the eroding Great Wall, we move to the world's most recognizable sporting venue, built by the Roman Empire. In 72 AD, the Emperor Vespasian began construction on a building that Rome had never seen before. He chose a deliberate location, the site of an artificial lake that had belonged to Nero, the previous emperor, who had seized a vast stretch of central Rome for his personal palace complex after the Great Fire of 64 AD. Vespasian drained the lake, cleared the land, and started building on it. The new building was to be funded by the gold and silver looted from Roman conquest in Jerusalem. The proceeds, along with 97,000 prisoners, were loaded onto ships and sailed across the Mediterranean. The same prisoners then broke ground on the largest amphitheater ever built, a structure that would become the most recognizable building the Roman Empire ever produced. The Colosseum took 8 years to build. When Titus, Vespasian's son, opened it in 80 AD, the celebrations ran for 100 consecutive days. It could hold between 50,000 and 80,000 spectators, making it the largest arena in the ancient world and larger than most stadiums built today. It was also one of the first major structures ever built primarily from concrete. The concrete they used was a mixture of volcanic ash, seawater, and lime called pozzolana. It was stronger than anything European builders would manage again for over 1,000 years. This enabled the Romans to construct curved walls and vast open spans at a scale that stone alone couldn't support. The exterior was faced with travertine limestone, fixed with iron clamps rather than mortar. Inside, the seating was arranged across 4 levels, with the social hierarchy of Rome reflected in where you sat. Senators occupied the front rows. The poorest citizens sat at the very top. Beneath the arena floor was an entire hidden city. A network of tunnels, corridors, and chambers ran under the sand where the events took place. This underground complex, known as the Hypogeum, was where the machinery of the spectacle operated. Gladiators waited in holding cells before their fights. Animals were kept in cages and lifted directly onto the arena floor through trapdoors, appearing suddenly in front of tens of thousands of spectators. Elaborate stage sets could be raised from below to transform the arena floor into forests, hills, or battlefield landscapes. The Romans engineered the Hypogeum with the same precision they brought to their roads and bridges, and it worked so effectively that the arena above it could be reconfigured between events without the crowd seeing how it was done. The gladiators who fought there occupied a strange place in Roman society. Many were slaves or prisoners of war, but a significant number were free men who volunteered. A successful gladiator became one of the most recognized figures in the city. The games continued for centuries. Emperors funded them, competed politically through them, and in at least one case participated directly. They became so woven into the fabric of Roman public life that they outlasted several significant political upheavals, continuing even as the empire itself began to weaken. By the 5th century, the Western Roman Empire was coming apart. The money that had funded the games for centuries was no longer available, and the events became less frequent. The last recorded gladiatorial combat in the Colosseum took place around 435 AD. Animal hunts continued for another 100 years after that. Then, those also ended. The arena fell silent. What followed was a slow process of dismantling that went on for centuries. Earthquakes in 847 and 1349 caused significant structural damage. The marble seating was stripped out and repurposed. The iron clamps holding the limestone together were pried from the walls, leaving the pockmarked surface visible on the exterior today. Large sections of the outer wall collapsed or were demolished. Medieval families built houses inside the remaining structure. At various points, it was used as a fortress, a cemetery, a Christian shrine, and a quarry for building material that went into the construction of St. Peter's Basilica and other major buildings across Rome. By the 18th century, enough of it had been taken apart that serious efforts began to preserve what remained. Pope Benedict XIV consecrated the site in the 1740s, which slowed the removal of materials. Restoration work began in the 19th century and has continued in various forms ever since. What stands today is roughly 2/3 of the original structure. The entire south outer wall is gone. The interior seating has almost completely vanished. The wooden arena floor, which covered the hypogeum below, rotted away long ago, leaving the underground chambers fully exposed and visible to visitors walking through the site. Despite what's missing, the scale of what remains is still difficult to process in person. The outer walls rise 48 meters. The footprint covers 6 acres. The building is so large that for centuries after it was abandoned, people living in Rome simply incorporated it into the city around it, building against its walls, sheltering inside its arches, using it as a landmark the way you'd use a hill or a river. It has been standing, in one condition or another, for nearly 2,000 years. The city around it has been invaded, rebuilt, burned, and transformed beyond recognition multiple times over. The Colosseum has outlasted all of it. In 2023, a new retractable wooden arena floor was installed for the first time since the Middle Ages, allowing events to be held on the surface again. 7 million people visit the Colosseum every year as it remains the most recognizable sports venue in history. To one recognizable monument to another, we move to India, to one of the most visited destinations in the world. In 1631, the Mughal Emperor Shah Jahan was on military campaign in the Deccan region of central India when a messenger reached him with news from home. His wife, Mumtaz Mahal, had died during childbirth. She was delivering their 14th child. Shah Jahan returned to Agra, and within a year of her death, he had begun making plans for a tomb. What he built over the next 2 decades became the Taj Mahal. Construction began in 1632 on the southern bank of the Yamuna River in Agra. Shah Jahan assembled a workforce of around 20,000 laborers drawn from across India and Central Asia, along with architects, calligraphers, and specialists in stonework from as far away as Persia and the Ottoman Empire. Materials came from across the known world. White marble was quarried from Makrana in Rajasthan, around 400 kilometers away. Jade came from China, turquoise from Tibet, sapphires from Sri Lanka. In total, over 1,000 elephants were used to transport materials to the construction site. The Taj Mahal is often described simply as a tomb, but that description undersells what Shah Jahan actually built. The complex covers 17 hectares and includes a main gateway, a mosque, a guest house, formal gardens, and the mausoleum itself. Everything was designed as a single unified composition, with the mausoleum at the far end so that visitors approaching through the gateway see it framed perfectly in the archway before they ever reach it. The mausoleum sits on a raised marble platform at the edge of the river. Its central dome rises 73 meters above the base, surrounded by 4 smaller domes and 4 minarets positioned at the corners of the platform. The minarets are built with a slight outward lean, so that in the event of an earthquake or structural failure, they would fall away from the main tomb rather than onto it. The white marble of the exterior changes appearance depending on the time of day and the quality of the light, shifting from pink in the early morning to bright white at midday to a pale gold at sunset. At night, under a full moon, the entire structure takes on a bluish tint. The interior walls are covered in pietra dura, an inlay technique using precisely cut semi-precious stones set directly into the marble to form intricate floral and geometric patterns. The craftsmen who did this work cut thousands of individual stone pieces, some of them just a few millimeters across, and fitted them together with no visible gaps. A single flower motif on the interior walls can contain over 60 separate pieces of stone. The level of detail throughout the interior is consistent from the floor to the ceiling, in corridors that most visitors pass through in a matter of seconds without looking up. At the center of the mausoleum, in a chamber beneath the main dome, sit 2 cenotaphs, decorative caskets representing Shah Jahan and Mumtaz Mahal. The actual graves are located in a lower chamber directly below, at garden level, following Islamic tradition that burial should be in contact with the earth. Mumtaz Mahal's grave is positioned at the precise center of the entire complex. Shah Jahan's grave, added after his death, sits slightly to the side, the only asymmetric element in an otherwise perfectly balanced structure. That asymmetry was unplanned. Shah Jahan had not intended to be buried in the Taj Mahal at all. His original plans called for a second mausoleum across the river, built in black marble, connected to the Taj Mahal by a bridge. The two structures would face each other across the Yamuna, white and black, his tomb and hers. However, construction on the Black Mausoleum never began. In 1658, before the second structure could be started, Shah Jahan was deposed by his own son, Aurangzeb, who seized the throne and imprisoned his father in Agra fort. Shah Jahan spent the last 8 years of his life confined to a room in that fort with a view across the river to the Taj Mahal. When he died in 1666, Aurangzeb had him buried beside Mumtaz Mahal in the tomb he had built for her, which is why the perfect symmetry of the interior has that one deviation. His cenotaph was added into a space that was never designed to hold it. The Taj Mahal took 21 years to complete. The construction cost, in contemporary estimates, equates to roughly $1 billion. When it was finished in 1653, it represented the full creative and financial resources of one of the wealthiest empires on Earth, directed toward a single structure for 2 decades. Over the following centuries, the complex went through significant periods of neglect. During the period of British rule in India, the gardens were redesigned in a more formal English style, altering the original layout. During both World Wars, the Indian government erected scaffolding around the main dome to disguise it from potential aerial attack, a precaution taken again during the Indo-Pakistani Wars of 1965 and 1971. The white marble has also been affected by air pollution from vehicles and a nearby iron foundry, which operated for decades close enough to the site to cause visible yellowing of the stone. The foundry was eventually shut down following a Supreme Court order in 1996, and ongoing restoration efforts have worked to clean and preserve the marble since then. Around 8 million people visit the Taj Mahal every year, making it one of the most visited monuments on Earth. Moving on, we will feature some of the most impressive lost cities in history. High in the Andes Mountains of Peru, nearly 2,500 meters above sea level, lies a city that was never meant to be found. Hidden between sharp mountain peaks and surrounded by thick cloud forest, Machu Picchu remained invisible to the outside world for centuries. No Spanish soldier ever recorded destroying it. No colonial city was built on top of it. It simply vanished into the mountains. At its peak, around 500 to 700 people lived in these ruins permanently, and no one knows exactly what it was. Some say it was a royal retreat for the Inca emperor. Others say it might have been a religious site with its temples, astronomical alignments, and sacred stones pointing to spiritual significance. For some, it was simply a hideout in case of a war. However, the most fascinating part about these ruins is their incredible construction that has preserved them for centuries. Machu Picchu was built in the 15th century during the height of the Inca Empire. At the time, the Inca controlled a vast territory stretching along the western edge of South America. They had no written language in the traditional sense, no iron tools, and no wheeled transport. Yet they built one of the most astonishing mountain cities in human history. The city sits on a narrow ridge between 2 mountains, with a river curving far below. On 3 sides, steep cliffs act as natural defenses. From a distance, the site is almost invisible, blending into the surrounding peaks. But building a city set in stone would have been extremely difficult. There are no nearby flat plains, no easy access roads. Every stone had to be shaped and positioned on a steep mountainside prone to earthquakes and heavy rainfall. To fight the elements, the Inca used a method called ashlar masonry. Massive stones were cut and shaped so precisely that they fit together without mortar. No cement, no glue, just stone against stone. Some blocks weigh several tons, yet you cannot slide a paper between them. This wasn't just an aesthetic detail, it served a purpose. The Andes region is seismically active. When earthquakes hit, the tightly fitted stones can shift slightly and then settle back into place. That flexibility has protected the city from collapse for centuries. But how did they move those stones? The Inca had no horses, no oxen, and no wheels for transport. Most likely, workers dragged stones using ropes and wooden logs as rollers. Thousands of laborers may have been involved, organized under a system known as mita, a form of state labor tribute. Citizens would contribute labor to imperial projects instead of paying taxes. And then there's the engineering beneath the surface. About 60% of Machu Picchu is underground. The visible terraces and buildings are supported by deep foundations made of layers of stone chips and gravel. These layers act as drainage systems, preventing rainwater from destabilizing the structures. In a region that experiences heavy rainfall, that drainage system may be the reason the city still stands. The agricultural terraces also served multiple purposes. They created flat land for farming, prevented soil erosion, and stabilized the slopes. Every level of the city reflects careful planning. Less than 100 years after Machu Picchu was built, the Inca Empire came under siege from the Spanish. The invaders destroyed every city in their wake, aiming to leave no trace of what was once a burgeoning civilization. However, they could not find Machu Picchu. That's because as soon as the residents heard of the Spanish invasion, they abandoned the city. However, they wanted to protect the city, possibly with a plan to return one day. They burned all records of what they built along with the surrounding forests and any paths that could lead up the mountain. Machu Picchu remained hidden for centuries. That was until 1911, when a Yale historian named Hiram Bingham arrived in Cuzco in hope of discovering the lost city of Vilcabamba. Bingham met with a local farmer who pointed the expedition towards these ruins sitting on a mountain. Bingham called it the Lost City of the Incas, but was later popularized as Machu Picchu. Since then, Machu Picchu has become a global icon. Millions visit each year, climbing the same steep paths once used by the Inca. The government has had to limit entry to 5,000 people to slow the erosion of the stones that have endured centuries of massive earthquakes and heavy rainfall. Imagine you're a spice merchant somewhere around 50 BC. You've just spent 3 weeks crossing the Arabian desert with a camel train loaded with frankincense and myrrh, goods worth more per ounce than gold in Rome. You're exhausted, you're filthy, and then your guide leads you into a narrow crack in a canyon wall. The passage is so tight your camels barely fit. The walls tower 80 meters on either side, and for nearly a kilometer, there's nothing but shadow and the sound of hooves on stone. Then the canyon opens, and carved directly into the rose-red cliff face in front of you is a building the size of a 12-story tower. Columns, friezes, statues, intricate decorative reliefs, all cut from a single continuous wall of rock with a precision that rivals anything in Athens or Alexandria. That was the treasury, and it was just the front door. The people who built Petra were the Nabateans, originally desert nomads who figured out something everyone else had missed. The ancient world ran on incense. Frankincense and myrrh weren't just for temples. They were used in medicine, in embalming, in perfume, in virtually every religious ceremony from Egypt to Rome. And all of it came from southern Arabia. The Nabateans controlled the trade routes north. They didn't just move the goods, they taxed them. Historical records suggest they levied around 25% on imports passing through their territory. By the 1st century AD, Petra's population had swelled to somewhere between 20,000 and 30,000 people, a significant city by ancient standards, buried deep in the mountains of what is now southern Jordan, and they built it in a way that had almost no precedent in the ancient world. Almost every civilization builds upward. You lay a foundation, stack materials, raise walls, add a roof. The Nabateans did the opposite. They looked at a cliff face and carved inward and downward, removing stone rather than adding it. The treasury wasn't constructed, it was excavated. The stonemasons started at the top. Engineers would identify the section of cliff they wanted and climb to where the roofline would eventually be. From there, working level by level with pickaxes and chisels, they carved a narrow ledge across the full width of the facade, essentially creating a blank canvas in the rock. Then they worked downward, tier by tier, cutting each column in sequence from above. The whole facade, 40 meters tall and 28 meters wide, with 2 full stories of columns and sculpture, was carved without ever building upward from the ground. Estimates suggest the treasury alone took somewhere between 3 and 4 years to complete, with teams of masons working simultaneously across different sections of the face. And the stone they cut away wasn't wasted. It was carted across the city and used to build Petra's freestanding structures. Across the canyon walls of Petra, there are over 800 monuments carved in this same tradition: tombs, temples, a theater with seating for 8,500 people cut directly into the hillside. The city is essentially a mountain that was hollowed out from the inside. The water engineering was arguably as impressive as any of the carvings. Petra sits in a desert that receives on average less than 90 millimeters of rain per year, about the same as the driest parts of the Sahara. And yet, at its peak, it supported a population of up to 30,000 people, plus the constant flow of caravans arriving with hundreds of camels that each needed significant water just to function. The primary supply came from 9 natural springs scattered across the surrounding mountains, the main one located about 7 kilometers from the city center. The Nabateans carved channels and laid over 200 kilometers of ceramic pipeline to route that water downhill into Petra. The cisterns were carved into the bedrock, plastered watertight, and deliberately concealed to protect them from evaporation and from any potential invaders. The Zuraba Reservoir near the city entrance was large enough to hold roughly a 3-week water supply on its own, ready to be released when a large caravan rolled in. And then there was the flood problem. The same mountains that fed Petra with precious runoff also funneled catastrophic flash floods down the canyon every winter. So the Nabateans built a diversion dam and a tunnel at the canyon entrance to intercept those floods and redirect them before they ever reached the city. When archaeologists excavated the Siq in the 20th century, they found the ancient flood tunnel still there. In 2018, when the tunnel was no longer maintained, a single winter storm sent a flash flood through the canyon that killed several tourists. The system had worked for 1,000 years. Without it, the city simply couldn't have existed. The Romans eventually absorbed the Nabatean kingdom in 106 AD, but Petra continued functioning as a major hub for another 2 centuries. What finally killed it wasn't conquest. It was a catastrophic earthquake in 363 AD, followed by a gradual shift in trade routes as sea lanes replaced overland caravans. By the 7th century, the city was largely empty. The local Bedouin knew it was there. To the rest of the world, it had ceased to exist. For roughly 1,000 years, that's how it stayed. In 1812, a Swiss explorer named Johann Ludwig Burckhardt heard rumors of a lost city in the Jordanian mountains. To gain access, he disguised himself as a Muslim pilgrim making a sacrifice at the tomb of the prophet Aaron, which happened to be located just above Petra. His guide led him through the same narrow canyon the spice merchants had used 2 millennia earlier and out into the same view. He was the first Westerner in recorded history to see it. Today, around 1 million tourists a year make that walk. In 2024, archaeologists excavating beneath the treasury found a tomb containing 12 skeletons, the building's original occupants, finally identified after 2,000 years. Most of Petra is still unexcavated. The Nabateans left over 800 carved monuments in these canyon walls, and the majority of what lies behind them has never been touched by a modern shovel. In 1922, Brazil was preparing to celebrate 100 years of independence. Across the country, there were debates about identity, faith, and the future of a rapidly modernizing nation. Out of that moment came an idea, bold, visible, and impossible to ignore: a giant statue of Jesus Christ overlooking Rio de Janeiro. Today, Christ the Redeemer stands 30 meters tall atop Mount Corcovado, with arms stretching 28 meters wide. Including its pedestal, the monument rises over 38 meters above the mountain peak. From below, it appears almost weightless, hovering above the city and the Atlantic Ocean beyond. The original concept was very different. Early sketches showed Christ holding a cross in one hand and a globe in the other, a more traditional religious pose. However, engineers wanted it to be more unique. The final design shows Christ with open arms, forming a giant cross shape. It's welcoming, protective, and visible from nearly every part of the city. It was transformed from a religious monument to a national symbol standing with open arms in a country balancing tradition and modernity. But building something of that scale in the early 20th century was anything but simple. The man behind the engineering challenge was Brazilian engineer Heitor da Silva Costa. The sculptural design was developed by French artist Paul Landowski. But the statue itself was not fully built in Brazil. Instead, the design was first modeled in clay in France. The pieces were then carefully transported across the Atlantic to Rio de Janeiro. From there, the parts had to be moved up Mount Corcovado, a steep 700-meter-high granite peak. There were no heavy-lift helicopters in the 1920s. The builders used an existing railway that had been built decades earlier to carry materials up the mountain. From the railway station near the summit, workers transported the pieces manually to the construction site. At first, the statue was planned to be made of reinforced concrete only, but pure concrete would crack and weather quickly in Rio's tropical climate, strong sun, heavy rain, and frequent lightning strikes. So, engineers chose to cover the concrete core with thousands of small triangular tiles made of soapstone. Soapstone is durable and resistant to heat. It also gives the statue its smooth, pale appearance. Workers spent years attaching these tiny stone tiles by hand. Each one was placed individually. If you look closely today, you can still see the mosaic-like surface. Construction officially began in 1926. For 5 years, crews worked on the mountain, battling wind, rain, and limited access. The arms were particularly difficult. Extending 28 meters across, they required careful balance and internal reinforcement to ensure they wouldn't sag or collapse. In 1931, the statue was finally completed. At the inauguration ceremony, engineers attempted something ambitious, lighting the monument remotely from Rome. But the technology failed due to bad weather, and the lights were switched on manually instead. When the new 7 Wonders of the World were chosen in a global vote in 2007, some critics questioned its inclusion. Compared to ancient cities or massive defensive walls, the statue is relatively recent. It was completed in the 20th century. It does not represent a lost civilization or an ancient empire. So why is it on the list? Supporters argue that its impact goes beyond engineering complexity. It has become a global icon. For millions of people, it represents faith, hope, and Brazilian identity. Its silhouette defines Rio de Janeiro as much as its beaches or mountains. There are also misconceptions about the statue. Despite different claims, it is not the largest Jesus monument in the world. Standing at 61 meters tall, the Jesus Christ the Savior statue in North Sumatra, Indonesia, inaugurated in September 2024, is the tallest Jesus statue in the world. Meanwhile, the 52.5-meter-tall Christ the King statue overlooking Lake Toba in Poland comes in second. And despite popular belief, it is not a completely Brazilian creation. It was, in fact, a collaboration between continents, even if its identity remains deeply Brazilian. Unlike Machu Picchu, which was hidden for centuries, Christ the Redeemer was designed to be seen. Its impact on Rio de Janeiro is undeniable. The statue has come to define the city and has become an important part of the culture. Almost 2 million people visit the site every year because of its spiritual hold on millions across the world. Did the aliens really build the pyramids? Have America's vintage bridges fallen behind China's modern structures? Comment your thoughts below. From construction wonders through history, move over to what the world is building today and watch our compilation of the biggest megaprojects under construction in 2026. Keep following Signum, and we will see you next week with another compilation of the most insane mega builds from around the world.